Hello, good morning, and welcome to a video presentation on data structure and algorithms project work. Our topic is bin packing problem using two dynamic algorithm and optimizing a final algorithm. I am Sauvik Mukherjee and my friend Subhranshu Bose will be present here to explain you about our project work.
So the project topic that we have, the bin packing problem, is one of the most common problems that are used we encounter in everyday life. What happens in this is that the objects of different volumes must be packed into a finite number of bins or containers, each of volume B, in a way that minimizes the number of bins used. In computational complexity problem, so this is a variant of a non-deterministic polynomial time problem. So as we have already discussed the applications, this is usually used for loading trucks, for Amazon packing system that we may come across, and it can also be seen as a special case of the cutting stock problem or the knapsack problem that are usually dealt with in everyday life. So as such, there are multiple algorithms to solve the bin packing problem. A class of algorithms called the heuristic algorithms, which include the first fit, or the next fit, or the best fit. So these are used usually to tackle it, as these algorithms produce a near optimum solution, and which a polynomial time algorithm doesn't. So the purpose of our project is to create a near optimal algorithm from the existing ones that we already have. The existing ones are the first fit or the next fit that we have worked with, and using and measuring the space and the time complexities of both of these algorithms in effect to the problem in question, we have developed, or we are developing, a near perfect algorithm. For this purpose, we have used dynamic programming. Dynamic programming is the main basis of our project, and it is nothing but a type of programming that uses functions and recursive ones at those to store and reuse values so as to reduce runtime and save memory as well. Now, comparing the efficiencies and drawbacks of them both, that is both the heuristic algorithms, we made a third near optimal bin packing solution. The bin packing problem, on the other hand, is an important problem which requires the sorting of items to a certain value into bins in a certain volume. Now, dynamic programming is a very powerful technique to solve a particular class of problems. It demands very elegant formulation of the approach and simple thinking, and the coding part is really simple and easy. It actually, in layman's terms, it could be said that joining or breaking down a particular problem into multiple subparts and then finding the solution of each of them, and hence aggregating all of them into a single solution. The idea is very simple. If you have solved a problem with a given input, then save the result for future reference so as to avoid solving the same problem again. So a DP algorithm technique, which is usually based on a recurrent formula and one starting states, a sub-solution of the problem is constructed from previously found ones. DP solutions have a polynomial complexity, which assures a much faster running time than other techniques like backtracking, brute force, etc. So an existing method and need for an optimal algorithm. So when we usually discuss this, we come across the ones that we have already used, or the ones previous people or previous studies have included, such as the first fit or the next fit. Now, comparing these, we found out that the time complexity, that the time and the memory usage is pretty high, and there is a scope to minimize this exponential time that we found out in our study. And this was only possible by using dynamic programming. We have stated the general algorithm for bin packing that is mostly used, And we have discussed, or we have reached the stage of discussing that next fit. That's the first algorithm we have used, and the first fit algorithm. Using this, we will create, by the end of our project, a near optimal solution, giving the solution in reduced time and maintaining the limited memory as well. So there are many applications to bin packing problem. So to better understand it, I'll state a few. So for example, the first thing that comes to mind is placing computer files with specified sizes into memory blocks of fixed size, or recording of all of a composer's music, where the length of the pieces to be recorded are the weights, and the bin capacity is the amount of time that can be stored on the audio CD. For example, about 80 minutes. One part of mathematics is that, having abstracted the problem of packing bins with weights, there are many situations to which mathematical techniques apply. So that once we have, say, the first fit heuristic, it can be used in these different situations. We can go ahead and look for problems where bin packing and algorithms which have been developed to get insights into this problem and be put to use.
Description about the next fit algorithm. As we know, in a bin packing problem, we need to arrange the weights in a bin such that we use the least number of bins. Now, talking about the next fit algorithm, it is an unfit and poor working algorithm, as in this algorithm we take our inputs in a for loop and put it in a bin, and if the bin is empty, or if it is having a space to put the input which we have entered, it will put it in that. If there is no space, it will directly take a new bin. So in this procedure, if there is a bin with empty space, that would be ignored. So it is a very basic code with a for loop, taking the input and incrementing the value of the number of bins if there is no space available in the bin which we have taken right now. So suppose we have taken a bin whose weight is 15 and our weight is 7, so it will get fitted in that. So number of bin is 1 in this case. So if the next input is 5, then we have total as 12. So in this case also, the next weight will come in the first bin itself, so we do not need a second bin. So the counter here will not increase. So the counter here is the RES. The counter will not increase. It will only increase in a case where our weight is exceeding the limit of the bin. So suppose after 12, if we put a weight of 5, so we will have 17 net weight. That will not be possible to put in the first bin, so we have to go for a new bin. So this is the general idea in the first programming, that is next fit algorithm. So this is not a good algorithm, as it requires only big O of n time and big O of 1 extra space to process the items. So it basically uses a for loop and puts the weight in the bin it is having. So there is no rechecking in this procedure. So we have developed the first fit algorithm. In the first fit algorithm, we have 3 inputs which we put in a method, that is weight, number of input, and the bin capacity. In this situation, we are having 2 for loops inside our definition, or the method first fit definition. So the first for loop iterates through the number of weights which we have, and the second for loop searches for the bins. It starts from the first bin, and if it sees if there is space available in any of the bin in which the weight could be put away. So this is a very good algorithm, because it sees that the number of bins which we are having gets filled. But in this situation, we do not see the optimum bin in which the input should be filled. Suppose if we have 5 bins which are filled, partially filled, and one of the bin is having a space of 5 and another bin is having a space of 2. Now if we have an input of 2, in our code of first fit, it will put that weight in the first bin that is occurring in its way, that is the 5, a bin with space 5 left. But the most suitable algorithm is to put it in 2. So in our next programming, the most optimal code, we will try to see that the weight that we are putting goes into the bin that is having the optimal amount of space for the weight that we are taking. So in this code we have two for loops. The first for loops iterates over the number of weights which we are putting, and the second for loop iterates through the bins. So whichever bin is having space initially, it will put the weight in that bin, and the res value will get incremented and we return that value. That value is the number of bins which we need in this case. So we have given two examples. We have entered the same input, that is the same number of weights and the same bin capacity for our two cases of next fit and first fit. So we have displayed the output as shown by the compiler in both the cases, and we have also added certain descriptions like the time complexity and space complexity in both the cases. The complexities in the second code is more, but it is more optimal because our main aim is to reduce the number of bins, which we can easily achieve in a second algorithm. Thank you.